We're surrounded by medicine, from the aspirin you pop for a headache to these incredibly complex, life-saving cancer drugs. But have you ever really stopped to wonder how they actually work? Well, that's the science of pharmacology. And today, we're going to dive into what it is, where it came from, and why it's facing a bit of a crisis today. Right? It's a question we've all had. You swallow a pill, and maybe half an hour later, your headache is just gone. But what did that little chemical actually do? What was its journey through your body to make that happen? That incredible, invisible process is exactly what pharmacology is all about. Okay, so let's get right to it. What exactly is pharmacology? To really get a good handle on it, it helps to look at how the founders of the field thought about it. This quote is from the preface of the very first major pharmacology textbook back in 1941. And the key phrase here is that last part: applications of pharmacodynamics to therapeutics. See, right from the very beginning, this wasn't just about making a list of chemicals and what they do. It was all about understanding how they work inside our bodies so we can actually use them to heal people. It's the why and the how behind every single prescription. So, to put it simply, pharmacology is the science of how drugs interact with living things. I like to think of it as the complete biography of a drug. Where did it come from? What does it do to the body? Just as important, what does the body do back to it? And how do we use it to fight disease? And that word drug is super broad here. We're talking about any chemical that affects our cells, from something as common as caffeine to the most advanced gene therapies out there. Now, while the formal science is pretty modern, our use of drugs is, well, it's ancient. The story of pharmacology is this amazing journey from just noticing what plants do to actively designing brand new molecules in a lab. For thousands and thousands of years, pharmacology was really just good observation. People noticed that the juice from a poppy could make pain go away. They saw that a certain vine sap on the tip of an arrow could paralyze an animal. And my favorite one, they supposedly discovered coffee by watching goats eat these specific berries and then stay up all night, just full of energy. These plants weren't just scenery. They were the world's first pharmacies, and they were packed with powerful chemicals. Okay, so this timeline shows the huge turning points. For centuries, we just used the whole plant. But then, in 1806, this guy, Sir Turner, doesn't just use opium, he isolates morphine, the pure chemical that was actually doing the work. That was a massive leap. Then, about a century later, Paul Ehrlich starts asking how it all works. He comes up with this idea of receptors, like tiny locks on our cells. And then, in the 1930s, Gerhard Domag finds that a simple dye can kill bacteria, and boom, the age of antibiotics is born. This is where modern drug science really begins. And that brings us right up to the modern era, because now creating drugs is so much more than just observation or happy accidents. It's a deliberate, methodical process of invention. This is probably the most important shift to understand. We don't really discover drugs in nature anymore, not like we used to. We invent them. Scientists now start by understanding a disease on a molecular level, finding that biological lock, and then they meticulously design a chemical key to fit it. It's pure creation. So to give you a sense of the sheer scale of this invention process, just look at this number. 10,000. That's a rough estimate of how many different chemical compounds might get made and tested at the very, very beginning of the search for just one new medicine. And this slide shows you the absolutely brutal journey that drug has to take. You start with, let's say, 25,000 different compounds in basic research. Almost all of them fail right away. The handful that look promising move on to testing in animals. From that group, maybe 5 to 10 are safe enough to even try in a small group of healthy people. Then, after years and years of more testing in actual patients, you are unbelievably lucky if just one of those original 25,000 compounds makes it all the way to approval. It's a process that can take a decade and cost billions of dollars, and the failure rate is just staggering. Okay, so let's say a drug finally makes it through that entire gauntlet and gets approved. What happens when you actually take it? Well, its interaction with your body is this really dynamic two-way street. And pharmacology breaks this down into two fundamental ideas. This is one of the most important concepts to get. On one side, you have pharmacokinetics. That's all about what your body does to the drug. It's the journey, how your body absorbs it, moves it around, breaks it down, and finally gets rid of it. Then you have pharmacodynamics. That's what the drug does to your body. It's the mission. What does the drug actually do when it gets where it's going? How does it produce its effect? You absolutely cannot understand a drug without understanding both sides of that coin. So we have all this incredible historical knowledge. We have this powerful scientific process. You'd think we're in a golden age, right?
Well, this leads us to a really strange and honestly pretty urgent problem facing pharmacology today.
You would think that with all our new technology, with mapping the human genome and everything else, that we'd be cranking out new miracle cures left and right. But we're not. The shocking reality is, creating truly new and innovative medicines has actually gotten harder and slower than ever before. And this chart just lays the problem out in the starkest terms possible. Take a look at the bar on the left. That's R&D spending. It has gone through the roof. Billions and billions more are being spent every year. Now look at the bar on the right. That's the number of new drugs getting approved. It's basically flat, and in some recent years, it's actually gone down. We are throwing way more money and resources at the problem than ever before, and we're getting less back. This is what's known as the productivity paradox, and it is a massive challenge for modern medicine.
So this leaves us with this really big, critical question. As our science gets more and more powerful, why is inventing medicine getting so much harder? Have we already picked all the low-hanging fruit? Are the diseases we're trying to tackle now just that much more complex? Figuring out the answer to this is one of the most important missions we have, because that engine of pharmacology, the one that started with people just watching goats eat berries, is what we now depend on to invent the cures of tomorrow. And right now, that engine